Okay, so we're going to take a look at section 1.5 today. So this section is on quadratic functions and transformations. So transformations is something we're going to study with lots of kinds of functions. The nice thing about them is once you learn kind of the general pattern of how transformations work, you can apply it to not just quadratic functions, but you can apply it to anything. Cubic functions, square root functions, trig functions. Right? So there's certain rules that we follow if you want to take a function and say shift it up or down, or left or right. So we're going to start to see some of those patterns today. So quadratic functions are written generally in the form ax squared plus bx plus c. B and c can be any number that you want, any real number. But what do you think a cannot be? Yep, John?
0.
Why not?
Because if it was on 0, then x would be equal to, or x squared would be equal to 0.
Okay, what's wrong with that?
That messes up the rest of your equation in a way that I have not fully processed yet.
Okay, so I do agree that a can't be 0, but why? Yeah?
Will the rest of it just be a line?
Yeah, if you make a 0, then what you have is f of x equals bx plus c, which is essentially y equals mx plus b. It's the same thing. It would just be a line. You would eliminate the quadratic term. All right, so a, b, and c can be any real number that you want, except a cannot be 0. That symbol there that looks kind of like an E, that means element of, or you could basically say it's in the set of. So A, B, and C are in the set of real numbers, but A cannot be 0. But anything else is fine. So let's graph y equals x squared, just see what it looks like. Clear that. And I'm also going to turn off the shading that we turned on earlier. Let's make it a solid line again. All right, and when you graph y equals x squared, you get that U shape. And what do we call that shape again? Yep, Julie? It's a parabola. Yep. So we get a parabola. Now, let's look at the difference between f of x compared to f of negative x. Okay. So that's, let me make that line actually a little thicker so we can see it. So we've got f of x squared. And now, let's see what happens if we do negative x squared. Let's hit graph. Any difference? No, exactly the same thing. What I technically did here is called a horizontal reflection. You put a negative on the inside of the function. So like, let's say you had an actual problem like 3x squared. If you do y equals 3, and you change the x to a negative x, that's a horizontal reflection. Horizontal reflection means you have flipped, like if this was your shape, that's a horizontal reflection. It flips left to right over the y-axis. But because the y-axis is a line of symmetry for the parabola, you can't tell that I flipped it. Right? Imagine just taking a piece of paper here on the y-axis and folding it right on the y-axis. The left side would land right on top of the right side, so you can't tell that it's been flipped. The only way you could tell if it was flipped is maybe if the parabola was moved over here, and then you did a mirror image, it would end up over here. Okay, but when the parabola is right on that y-axis, you can't tell that you flipped it. That's what the negative inside does, causes a reflection. Now when you have a parabola, it contains a low point, could also be a high point if the parabola was flipped over, and that's called the vertex. And we practiced finding a vertex yesterday when we had the rocket problem, and they wanted to know the maximum height that the rocket reached. We found the coordinates of the vertex. We did it using a graphical approach. You can also find the coordinates of the vertex using algebra. You could also do it using calculus. So there's lots of ways you can find the vertex of a parabola. So what I want to play with now is, let's see what happens if you put different numbers in front of the x squared. All right, so we've got y equals x squared. Let's graph 1/3 x squared and 2x squared. So the way you'd want to do it is like that. Put the 1/3 in parentheses because it was a fraction. The 2, I don't need parentheses. Let's compare the red and the black graph to the blue. So blue is the original. Let's see. There's one of them. That's the 1/3 x squared. And the one in black is going to be the 2x squared. Anybody describe what happened there? What did those different numbers in front of x squared do to it? Yeah. Yep.
The fraction stretched it and the whole number like compressed it.
Yeah, so it definitely causes things to stretch and compress. And the way we're going to think about it is vertically. So imagine that the original parabola in blue was like glued down right at the origin. Maybe it was like a strip of metal that was flexible. And imagine you took the ends of the U shape and started pushing down on it. What would happen to it is it would spread out and it would get wider. Right? Just like if you had clay and you push down on it, you compress it, it would spread out wider. Now, same idea. Imagine that it was glued down right at the origin, and you took those metal strips and you started pulling up on them. Right? If you pull up on it, it's going to cause it to get skinnier. All right? So what we really did here was called a vertical stretch or vertical compression. It depends on what kind of number you put in front of x. So the effect of changing a causes a stretch or a shrink, compression. You can say either way. And the key is if you put a number in greater than 1, it's going to cause your graph to stretch vertically. It's going to cause it to get skinnier because it's getting taller. If you put in a number in front of the x squared that's between 0 and 1, that's going to cause your graph to compress vertically. It's going to get squished down, which has the effect of making it look wider. And of course, the bigger the number you put in, the more of a stretch you can create for compression. If you graph like y equals 50x squared, that's going to stretch it an extreme amount vertically. If you put in like y equals 1/100x squared, that's going to make the parabola very squished, and it's going to start to get very wide horizontally. So any question on what a does to the parabola? All right, so now let's try this. A little different than the negative I did before. The difference is this versus that. I did this before. I replaced the variable x with a negative x. I'm not doing that in this one. What I'm doing this time is I'm putting a negative out in front of the function. So it's like I'm just taking the formula I had and then putting a negative in front of it. So let's see what a negative in front does. Does anybody have a guess? If you remember what the negative did when it was inside, it's similar when you put the negative on the outside. Tim?
Does it reflect across the x-axis?
Yeah, it's going to reflect it across the x-axis, which means a shape like that is going to end up looking like that. We call that a vertical reflection. Okay, I'm not going to graph all of them, but let's just do x squared. And I'll show you how you can type in a negative in front. What you could do is just press negative, vars, function, y1. So I'm graphing what y equals x squared, and then I'm graphing the negative of that. Honestly, doing it this way didn't save me a lot of time. If y1 was a really long and complicated formula, and I wanted to put a negative in front of it, this would save me from having to retype that really long and complicated formula. But in this case, you could just type it in negative x squared. It would have been just as quick.
How did you get that again? Why one?
You have to go to variables, y variables, and the first option is function.
Oh, okay, thank you.
Yep. So now I'll hit graph, and you're going to see the original. And then you're going to see the one in red flipped down below. Okay, so that's called a vertical reflection. And that's an easier one to see because when you do it, you actually see a result. The horizontal reflection, we didn't see a result because we reflected on the line of symmetry. Anytime you mirror image something on a line of symmetry, you can't see the result. So, what I want to do is look at two different parabolas. This is called the parent function. Okay, it's kind of the simplest parabola you can have. There's no other numbers in the equation. And I want to compare the parent function to y equals negative 5x squared. All right, so if we wanted to describe the transformations, there are two things happening. You always treat the negative and the number as separate things. So let's start with what's closest to the variable and work our way out. So, start with the 5. What is the 5 going to do to y equals x squared? Yeah, Caleb?
It's going to make the function steeper.
Yep, and how did we describe it?
Vertically stretched.
Exactly. So we're going to say vertical stretch. That's part of it. But now say how much? By a factor of 5. Vertical stretch by a factor of 5. So that's what that does. And how about the negative? What's that going to do? Yep, go ahead.
Reflects it over the x-axis.
Exactly. Reflect over x axis. So that's what they mean by how does the graph given first come from the graph that I have the box around. Any questions on that? Now, there is a certain order that's important, and we're going to talk about that, especially when you have multiple transformations. Like let's say you had a shift up one, shift left to a reflection over the vertical axis, and then a vertical switch. You have to list them and perform them in a certain order, just like when you do arithmetic, you have to do it in a certain order, like PEMDAS. Okay? Otherwise, you get a different result. So we'll talk about that order in a little bit. All right, let's look at this one. So now I'm adding a number. Okay, Okay, I'm not multiplying by a number. So let's start with the x squared plus 2. So what I could technically do is this. Take the original function I had, and then just add 2 to it. Or just type in x squared plus 2 from scratch. That's fine. Anyone have a guess what the plus 2 is going to do? Nick?
I think it horizontally shifts it.
I do agree it's going to be a shift. So the only question is it going to be horizontal or vertical? And then once we know that, there's always 2 directions. Vertical is up and down. Horizontal is left and right. Yeah, Sophie?
Would it be vertical up too?
Yeah, this one actually is going to be a vertical shift up 2. So the key is when you add something outside of the function, it moves it up and down. Okay? And what I mean by outside is what I have there. That's adding inside the squared function. That's going to do something else. All right? So the plus 2 outside of the x squared caused it to move up 2 units. So how? So to get x squared plus 2 from y equals x squared, we're going to shift y equals x squared up 2. That's one way you could say it. All right, and then to get y equals x squared minus 3 from y equals x squared. What do you think you would do to get that one? How would you get x squared minus 3 from x squared? Yeah, Lindsay?
Shift y equals x squared down 3.
Yeah, shift y equals x squared down 3. Now, we never say shift down negative 3. You always shift a positive number of units. Up would be positive, down covers negative. So don't say something like shift up negative 5 units, or always shift a positive number of units that tell me the direction. So these are examples of vertical shifts. They're called rigid motion transformations because they don't stretch. All they do is take what you have and move it somewhere else. So if you have x squared plus k and k is greater than 0, it would shift up k units. If k is less than 0, it would shift down absolute value of k units. And I put the absolute value there, just like we did here. We didn't say shift down negative 3. We said shift down 3. Yep.
So in the quadratic function, this is c, or is this one b?
So what ends up happening, I think we might touch on this at the end, is your parabola has to be written. I think you're thinking of this.
Yeah.
Unfortunately, if your parabola is written that way, you can't tell the transformations easily. It has to be written something like this. A number, those are the 4 transformations we're going to look at. So if you gave me something like y equals 4x plus 2 squared minus 8, I can very easily tell you it's been shifted left 2, vertical stretch by a factor of 4, and then down 8. Now, if you FOILed this out, this x plus 2, and then distributed the 4 and subtracted the 8, it would turn it into this ax squared plus bx plus c, which wouldn't be helpful at all. So we have to, if we ever end up with something like, I'm just making this up. If you end up with something like that, you have to convert it so that it looks like this to be able to tell the transformations. So yeah, it's not always the C. All right, so this one is adding and subtracting again, but now it's on the inside. Anybody have a guess what the minus 3 is going to do? Which way? Yeah, Mike.
It's gonna move your line 3 points to the left.
Yeah, you might think, well, actually, let me think about that again. So I do agree it's going to be horizontal. Let's try it and see what happens, though. This one's a little tricky. So there's the original, and Michael said 3 units to the left, but the -3 actually moved it 3 units to the right. So this one, we've got to be a little careful. It's almost like the opposite of what you would think. Right? So to get y equals x minus 3 squared, you could say shift y equals x squared, right 3. Right, and the other one, to get y equals x plus 2 squared, we would shift y equals x squared, which way? To get x plus 2. Yep.
2 units to the left.
Yep. Shift y equals x squared 2 units right. Right. So this is another rigid motion transformation, but you've got to somehow keep track and remember that left and right. So there's different ways to think about it. I'll give you one way, and the way that I'm going to mention is to focus on the number that's after the minus sign. Okay? So if you had something like this last one, let's think of it like this. Minus minus 2. So what I'm going to do is I'm going to focus on the number that comes after the minus sign. So like in this bottom one, focus on that. In this one, focus just on that. So focus on what comes after the minus sign. Block everything else out. But don't hold it. Right? So that's a 3. Positive 3 if you block out everything before it. Positive would mean to move right 3. This bottom one, it was written as x plus 2. I said think of the number that comes after the minus sign. Well, there wasn't a minus sign. So I can make a minus sign by writing it minus minus 2. Then block everything that comes before the number. So it's like you block this part out and look at what's left. Minus 2. Minus 2 means to move 2 units to the... If you were confused, I understand why. 2 units to the left. Okay. So it's just however you can keep it straight, you have to kind of keep track of that. So if it's written in the form x minus h, focus on just the h part. Focus on what would come after the x minus. If what comes after the x minus is a positive, you're going to shift right. If what comes after the x minus is a negative, you would shift left. So that's one way to think about it. As long as you can keep it straight, however you want to keep it straight is fine. So, x minus 2. Block out the x minus. All I see is a 2. That means it would go right 2. X plus 3. Okay, don't have a minus. Think of it this way. Block out the x minus part and look at what's left. Minus 3. 3 units to the left. Any question on that? All right, so when we start shifting left and right, we're moving the line of symmetry. How about if we move up or down? Does that have any effect on the line of symmetry? No, because the line of symmetry for a parabola is vertical. So if you take a parabola that started here and shift it up, it's still the same line of symmetry. There's no change. So, what we can do is find the coordinates of the vertex after we shift it. So there's two things we have to focus on to find the new vertex. How much of a shift did you do left and right? And how much of a shift did you do up and down? So the coordinates of the vertex would always be h, comma, k. H takes into account any left and right movement. K takes into account up and down movement. If you don't shift it, then the vertex is always 0, 0. And I kind of hinted at this already, but which one of these two, H or K, has an effect on the line of symmetry? Yep, Annalise. So H is the only thing that has an effect on line of symmetry. Shifting up and down has nothing to do with the line of symmetry. So if you have to find the equation of your new line of symmetry, it's x equals, because it's vertical, and it's x equals however much you shifted left or right. X equals h. The vertical stretch would have an effect on the line of symmetry. Yes?
If you were to shift a parabola up a unit, would it ever intersect the parabola, the original parabola?
No. No, because as long as you don't change the width, the parabolas would never intersect. It would look like they're getting very close, but they would, the one that's shifted up would always be a very small amount bigger. Like if you shifted it up 1 unit. Now, because you're squaring, you start getting to x values in the millions, a difference of 1 is almost hard to see on the screen. One could be at 4,000, whatever, 4,000, and the other one could be 4,001 is a y value. So they look extremely close. All right, so let's look at this one and see if we can find the vertex and the line of symmetry. Let's start with the +2. Caleb, what's the +2 going to do?
+2 is going to shift it to the left.
Yep, 2 to the left. And what about the -3? Someone else? Yep.
It's going to shift it 3 units down.
So taking what he just said and writing the vertex, he said 2 to the left and 3 down. And that's my new vertex. Okay, line of symmetry. Sophie, how does the equation for our line of symmetry always start?
X equals
Always going to be x equals.
-2.
And in this case, it would have been x equals 0, but you shifted 2 units to the left. So now it's x equals -2. Okay, questions on that? So before we do that example, let's talk a little bit about the order that you should always perform transformations in. I'm not saying every problem will have this, every problem will have every one of these, but this is the order to generally follow. So you always want to start with your horizontal shifts, followed by vertical stretching or shrinking. Then any vertical reflections. And lastly is the vertical shift. We're not really gonna deal with horizontal reflection too much, because I showed you guys that earlier, how it looked the same, unless you did a shift at the same time. But if you did have a horizontal reflection, it would be right in here. You want to think of that as like 1A and 1B. We're not really gonna have 1B in this section, but it will come up in the future. Horizontal reflection or horizontal stretch. Again, we're not going to do that too much in this one. So really, just focus on 1, 2, 3, and 4. All right. So let's look at this one. So this one has multiple transformations, and the order that we name them is important. So, what number would we focus on first? You don't have to even tell me what it does yet. Yeah, John?
+4.
The +4, that's going to be the last thing that we focus on.
Oh.
Yeah,
Oh, the 5.
the 5. Right. And what does the 5 do?
Stretches it vertically.
Yep. So, there is no horizontal shift in this problem. So we go to the next thing. Is there a vertical stretch? Yes. So the first thing is a vertical stretch by a factor of 5. And the second thing is the +4. How about, Mabel, what's the +4 going to do?
Shift of 4 units up.
Yes. So shift 4 units up. And when you describe a transformation, you have to tell me what it is and how much it is. Vertical stretch, how much? Shift, how much? Which way? So shift 4 units up. Okay, any questions on that one? Yes. All right, let's try same thing here. So describe, we want to describe this one. First of all, I think your idea. How many transformations are happening here? Yeah.
3.
No, more than 3. Yeah. Go ahead, Mabel.
Would be 4.
Yeah, it is 4. 1, 2, 3, 4. All right, so let's describe them. And now we got them all, so we got to make sure we do them in the right order. What's my first transformation? Mike?
Your horizontal shift.
Yep. And in this case, how much? And which way?
1 to the right.
So that's going to be 1 unit to the right. So shift 1 unit right. All right. Second thing. Tim?
Vertical stretch by factor of 3.
Vertical stretch by factor of 3. Good. Factor of 3. All right. How about my third thing? Yep.
Reflect over the x-axis.
Reflect over the x-axis. And fourth thing. Yep, Sophie.
Shift 4 units up.
Shift 4 units up. Questions on that one? Now, that's the form that you wanted in, right? If somebody had taken this x minus 1 squared, FOILed it out, distributed the -3, and then added 4, that would mess it up. We wouldn't be able to tell the transformations. They'd kind of be buried into the equation. We would have to fix it so we can see them. So that's what we're going to do next. So if you are given an equation in the form ax squared plus bx plus c, that's not the way you want it to be able to describe the transformations. So the way we have to fix it is to complete the square. So I'm not going to, again, that's something we've done probably back in Algebra 1, Algebra 2. So we're not going to spend like a whole lesson on it, but I'll go through an example and show you what I'm doing at each step. So completing the square is just a way to rewrite your equation so it's in a way that's easy for us to see what the transformations are. So the key to getting it in the format that we want is when we complete the square, if we do something on one side, we have to keep it balanced and do it on the other side. So, the first one we're going to look at is 3x squared plus 12x minus 18. That's not how we want it written at all. We need to make that look more like this. Number in front, x plus or minus there, squared. I need to see what the numbers are in those boxes. And that's what completing the square will tell me. Okay, so as I do the step, I'll tell you what I'm doing. Most people don't remember this method as well because quadratic formula is used more often in Algebra 1, and so is factor. All right, so first thing we're going to do is you have everything on one side of the equation. That's usually how it starts if it's in ax squared plus bx plus c. And we're just going to replace y with 0. So we're setting it equal to 0. The second step is to put the constant on the other side. In this case, what's the constant? Julie? And how would you move that to the other side? Add 18 to both sides. Once you get a little more familiar with it, you can do kind of more than one step at once, but I'm showing each step. So from here to here, put constant, I'm going to say it like this, get constant alone. Next, to complete the square, you always want the coefficient of the x squared term to be a 1. Right now, what's my coefficient of the x squared? 3. So what I can do, and I'm lucky that I have a 12 here. If I didn't, I'd still have to do this. But I can factor a 3 out. Right? And it will factor out nicely because I had a 12. If that was an 11, I would still factor a 3 out. Okay? Because I have to make the coefficient of x squared 1. So make coefficient of x squared, make the coefficient of x squared equal to a 1. So then we're going to have 3. And that's going to leave me with x squared plus how much? Yeah?
4x.
4x. Okay, now we're ready to complete the square. So what we're we're going to do now is we're going to add something to both sides of the equation. This is where we have to keep it balanced. But we have to add something very special. And this is the whole trick. So I'm going to leave a little bit of room after the 18 because I'm going to add something. I'm going to have 3x squared plus 4x. And leave a little bit of room because you're going to add something there. All right. So the way you figure out what to add is you take the coefficient of the linear term. What's the coefficient of my linear term in the parentheses? Michael? 4. So we're going to take 4, and you do two things to it. Take the coefficient of the linear term, divide it by 2, and then square it. So take the coefficient of the linear term, divide it by 2, and square it. So Michael said it, we have a 4. What's 4 divided by 2? 2. Square it? 4. So just a coincidence that happened. If this was a 6, I would divide it by 2 and get 3, square it and get 9. Okay. Now, whatever I just added on the right, I have to add on the left. What did I just add on the right?
4.
Nope.
Oh, 12.
12. This is the part, when you have a number in front of the x squared, this is the part that can trip people up because you have to factor that out. Anything that you put inside these parentheses, including this 4, is really tripled. So you just added 4 times 3. Added 12 on the right, so you need to add 12 on the left. If the x squared had a 1 to start with, then you wouldn't have factored anything out, and that little tricky situation wouldn't have come up. All right. Any question why I added 12 on the left? And now from here, it's going to start to look like what we want it to look like. So let's combine like terms. And if you've done this correctly, this should factor very nicely. And it should factor into two things that are identical, like x plus 7, x plus 7, x minus 4, x minus 4. Does anybody see how x squared plus 4x plus 4 factors? Yeah, Lindsay?
X plus 2, x plus 2.
X plus 2, x plus 2. Instead of writing x plus 2, x plus 2, I'm going to write it like that. X plus 2 squared. So from here, what did I do? I simplified. Yes, I simplified and factored it. Simplify and factor. All right, let's put the constant back on the other side where it started. 3x plus 2 squared minus 30. So what did I do there? I just moved the constant back. Constant back. And the last step is to set it back equal to y, the way we set it equal to 0, but setting it back. So there is our equation. Now, what I can do is, just to see if we did that right, which hopefully we did, type it in on y1. Let's type in 3 times x plus 2 squared minus 30, and type the original problem in y2. What was it? 3x squared plus 12x minus 18. 3x squared plus 12x minus 18. If I did this right, these two graphs should look exactly the same. If they look different, then we mess something up. Okay, but these should be exactly the same problem, just rewritten in a friendlier way to see the transformations. So let's say graph. So what we're gonna see there, that's what we got. It goes off the screen, that's okay. We're just looking to see if the red graph traces right over it. And it does, perfect. So that means the two equations are exactly the same thing. This is just more readable for transformations. So, what is my first transformation happening in that equation? Yep.
What happened to the 4? Like, on the top there it says 3x and then plus 4, but then the next line is just like not there.
So we factored this. X squared plus 4x plus 4 was factored into x plus 2 times x plus 2. Because if you FOILed out x plus 2, you would get that back.
No, the 4 next to it. The one on the end.
This 4?
Yeah.
Yeah, so it was factored.
Oh, okay.
Because if you FOIL out x plus 2, x plus 2, you get x squared plus 2x plus 2x, and there's your plus 4 right there. 2 times 2.
Oh, okay.
So this was factored into that. Any question on that? You can always FOIL this back out, which doesn't mean square this and square this. To FOIL, you got to do all those steps. But if you FOIL that back out, you should get that back exactly.
Where did the 4 come from in the first place?
The 4?
Yeah.
We took the coefficient of the linear term, divided it by 2, and squared it. So there's the coefficient of the linear term.
Yeah.
I divided it in half, and then I squared it.
Okay.
That's the magic trick that makes this factor nicely. That's the completing the square part. Yep.
What's the rules for factoring again?
For factoring,
Yeah, like
so you really, well, if you're trying to factor it, generally this number is always going to be a 1 because it has to be. So that makes the factoring a little better than it could be. But you need to find two numbers that multiply to give you 2 and add to give you 4 in this case. If the signs were different, the rules could be a little different, but that's in general what you're looking for here. Only thing that could be different is this could be a minus. This always has to be a plus. Because when you square something, when you divide by 2 and square something, you're always going to get a positive number. So what's the first transformation that's happening there? Yeah, John?
It's a horizontal transformation.
So it is going to go left. What kind of transformation is it?
Horizontal shift.
Shift. So let's say shift left 2.
I was thinking translation.
Yeah, you could say a translation to you move 2 units to the left. You could say it that way. What's the second thing? Yeah, Caleb.
Vertical shift by a factor of 3.
Vertical stretch by factor of 3. Yep. And the last thing is shift down 30. So before we completed the square, you couldn't tell that this was shifted down 30 units at all. I mean, there's no 30 anywhere in there. Okay, so the only way to tell is to complete the square. All right, so that's the homework for tonight. Let me just check one thing. I will talk about that tomorrow. So we got up to, I think, number 41 or 44. If you have trouble with numbers 44 or 60, I forget which one it is, that's okay. But we'll mention something at the beginning tomorrow. In fact, what I'll do is I'll pause it, and after you guys leave, I'll put the note on the board so it's at least in the video. All right, so the last thing that we didn't get to is called the discriminant. And basically, what the discriminant is, if you think of an equation written in the form ax squared plus bx plus c, the discriminant is this expression. It's b squared minus 4ac. So when you do b squared minus 4ac, what that tells you is how many times the parabola crosses the axis. Anywhere that a graph crosses the axis is called a root or a zero. So there's really three cases. A parabola could cross twice. A parabola could come down, touch the axis, go back up. Or you could have a parabola that doesn't cross at all. So you could either have no zeros, in other words, no x-intercepts, one x-intercept or 1 0, or two x-intercepts, 2 zeros. And the calculation b squared minus 4ac tells you what case you have. It doesn't tell you where the roots are. It just tells you how many times it would cross the axis. So if b squared minus 4ac comes out less than 0, you have no root. If it comes out exactly equal to 0, then you would have one root, or 1 0, one x-intercept, all the same thing. And if it comes out greater than 0, you would have two x-intercepts, or 2 zeros. All right, so that's all that the b squared minus 4ac is used for. So, for example, in the homework, I think number 44 is the problem that's going to use the b squared minus 4ac. All right, so if you guys have any questions on that, we can take a look at that a little bit more tomorrow.